Thank you, Ronan, for the, sorry, can you hear me?
The screen is yours.
Okay. So thank you, Ronan, for the introduction. And also I would like to thank the organizers to make this conference happen. So a small story is that 8 years ago when PLMCN came to China for the first time, I was a PhD student of Shanghai, who is the host, and for sure I will be the volunteer. So I pick up speakers from the train station and deliver the microphones. So right now I became a speaker of this conference. So today I'm going to talk about our 3 works on the interlayer excitons in van der Waals heterobilayers. So those works were done in the at the University of Michigan, Professor Hui Deng's lab when I was a postdoc there. And recently I joined the Xiamen University. So everybody should be very familiar with monolayer TMDCs. It has very large bonding energy and a strong oscillator strength, and the very famous Valuetronics, which can be the degree of freedom can be addressed by optical pumping. And last but not least, the flexibility to integrate with any substrate and photonic structures and make it very easy to fabricate those devices. But not everything's perfect. For example, the value polarization in those monolayers characterized by photoluminance are generally pretty low. And the short radiative lifetime will make it harder to reach high density. And also in terms of device, lasing device based on monolayers are mostly designed on the photonic crystal, on the microcavity based on those quantum dot architectures. So the gain area is very small. So we try to find answers in heterobilayers. So what's new in heterobilayer? So in addition to the intralayer exciton in monolayer, you will have the interlayer exciton with electron hole separately into these 2 layers. So with that, you will have a reduced oscillator strength. So the lifetime is longer. For example, this paper reported the exciton condensate in the heterobilayers. And also with reduced electron hole exchange interaction, we hope to slow the valley depolarization rate. And the permanent dipole can induce very strong dipole-dipole interaction. You can start in many-body physics. And most importantly, because there is twisting or lattice mass missing, so there must be a Moiré superlattice, which will provide another platform to tune the exciton state. Okay, here are the 3 works I would like to deliver. So first is the high value polarization from the interlayer exciton emission. I need to emphasize that here there's no magnetic field. So we know that monolayer TMD hosts the Valuetronics, and it can be adjusted by optical pumping. You shine circularly polarized light and measure the co and cross polarized component. So here is the definition of degree of polarization. But even if you do it at a cryogenic temperature and do the near resonant pumping, so that you will always get the cross polarized component. So the depolarization is mainly induced by this kind of electron hole exchange interaction. So we know that in heterobilayer, when you align the 2 layers well, the key or key prime value between the 2 layers are aligned. So the interlayer exciton will inherit the Valuetronics from the monolayer. More importantly, the electron hole separation will, we hope to turn off this exchange interaction, whether it will be suppressed. So, but if you look at the reported value, it's still very low. So the main reason is like this. First, here is the equation describe the value polarization of your photoluminance, and the P0 is the initial polarization after the charge separation. The K parameter is this 2 time, and one is exciton decay time, the other is the value depolarization time. So the idea is you want to reduce this exciton decay time to make sure the value depolarization cannot happen so efficiently. And the other problem is in such a heterobilayer, the Moiré lattice play an important role. It might induce the minibands. So here is the theoretical results at different twist angles, you could have Moiré excitons, and even in the same K-value, so different exciton can couple with the opposite, with the photon of opposite helicity. So that means spin and valley are not locked anymore. So if your inhomogeneous is broad, it might cover several millibands, and you measure the valley polarization is the average value, so it cannot be high. So the similar reason is applied for the spin singlet and a triplet exciton, which I will talk about later. So the strategies are straightforward. You want to make sure this X as small as possible, so you need to precisely align the material to make sure it is close to a direct band gap transition. And secondly, you want to reduce the inhomogeneous problem. In that case, you can separate those mid-bands very well. We fabricated the sample, and this SHG polarization-dependent SHG indicated the rotation alignment is good, and we measured the line width is down to 10 MeV, and we checked the degree of polarization. To make sure our setup is correct, we tried both sigma minus pump and sigma plus pump, and make sure everything will be flipped. Indeed, it is. So here is the one example. You pump with sigma minus, you saw a very strong emission with co-polarized component, and at higher energy, you observed another peak with cross-polarized component. So both of them showed a very high degree of polarization, over 80%. And their energy difference is about 20 MeV. So which corresponded to the conduction band splitting of the mobilium diselenide. So the dynamics is like this: you pump at the intralayer exciton of the tungsten, and the electron will transfer to the other layer and populate at both bands, and they will recombine. So it's easy to understand the spin conserved transition, which corresponded to the singlet exciton, but the non-conserved triplet exciton is also brightened in such a heterobilayer. So this has been predicted by the theory group, and simply speaking, it's due to the outer plane mirror symmetry breaking. So the triplet exciton is brightened. So they calculated the oscillator strength for both singlet exciton and triplet exciton. So they find that the oscillator strengths at these atom registry are comparable. But most importantly, they will couple with a photon with opposite helicity, which represented by the different color. So this analysis fully agree with our observation. So in the time scale, we also checked these two time parameters. We found that the decay time is 2 nanoseconds, means that we make the rotation alignment is precise, and the valley depolarization time is 10 times longer. So that's why we observed a very high degree of polarization. Okay, so then we tried to integrate such a heterobilayer with a microcavity to demonstrate a lasing device. Before that, I would like to show those 4 works about Interlayer Exciton lasing paper. It's easy to understand when you found a direct bandgap semiconductor, you want to demonstrate some nano laser device. And those are the 4 results people demonstrated. But the evidence is they showed is based on the nonlinear increase of the output photon and also the reduction of the line width. But sometimes those are not very convincing evidence. For example, this review paper, they put all the 4 works together and put these criteria and see whether they satisfy all of them. So you will find that coherence measurements are missing in all of those experiments. So we know that coherence is very important feature for a laser device. And also in those monolayers, there could be defect trapped exciton, which cannot be excluded without spatial coherence measurement. So how about the interlayer exciton in heterobilayers? So for sure, the radiative rate for interlayer exciton is slower compared to the intralayer exciton, but it's still comparable with the gallium arsenide if you do the rotation alignment very well. So what's more is that in such a hetero-bilayer, you naturally create a three-level system. As I mentioned previously, the dynamic is you create Intralayer Exciton, the electron will transfer to the mobilium layer in femtosecond scale, and they will recombine through the interlayer transition. So you can reach the population inversion of this interlayer transition much easier because the intralayer absorption is very strong. So the pumping efficiency is very high. Okay, we decided to use such a one-dimensional grating structure to provide the optical feedback. That's the microcavity. And the good thing is that the field will extend it over the entire grating, so you can measure the spatial coherence much easier than the previous defect like a photonic crystal. And also we have a TE and a TM mode. So in this design, we make sure TE mode is in resonance with the interlayer transition, but the TM is far off the resonance. So in TM mode, there is a bare interlayer exciton emission, which could provide a good reference for the lasing. And here is the fabricated grating. We measure the Q is around 600, not quite high, but the field indeed from the simulation, it will extend over the entire grating. Here is the result, angle resolved photoluminance. We found that in the TE component, the interlayer exciton emission will efficiently couple to the cavity mode, but in TM mode, there is just a very broad emission from the interlayer exciton. We do the power dependence. We found the nonlinear increase of the output, which means the stimulated emission overcome the spontaneous emission. And also we found the line width narrowing indicate the temporal coherence increases. And then we decide to measure the spatial coherence, which is defined by this first order correlation function, the coherence between the position from R and minus R. So this can be measured from the Michelson interferometer. And one of the arm is the mirror is replaced by the retroreflector. It can flip the beam central symmetrically, and the R and minus R can be overlapped on the CCD. So such a G parameter will be integrated in the intensity information. And we change the delay of the arm, and we'll track the intensity at certain position. You will find this oscillation. You fit it with sinusoidal function. You can extract this correlation function at this position, which is proportional to the visibility. You can do it over the entire emission pattern and get the G1 distribution over the entire sample. And we do it over all the power we measured. Below threshold, we found that the spatial coherence is around 2 micrometer, and above threshold, it extended to 5 micrometer. This means that our lasing process is accompanied by the building of spatial coherence. Okay, so in summary, we demonstrated such an interlayer transition integrated with the grating, and it showed the lasing feature, and we can measure the extended spatial coherence. The future work could be focused on the Moiré lattice. Right now, we didn't explain the role of a Moiré lattice in such a device, which could play a very important role in the dynamics. And also the electrical injection can be implemented through this configuration. Okay, the third work is we are trying to demonstrate that the interlayer exciton can be tuned continuously by the twist angle in the heterobilayers. So the previous results are mainly focusing on this kind of type 2 band alignment. So the electron hole are separate into the 2 layers clearly. But in this kind of sample, you can only start it using the photoluminance because the oscillator strength is pretty small. But usually they could include the charged exciton or the defect trapped exciton. So it's very difficult to study the twist angle dependence of the interlayer exciton, which is predicted by theory. It can be continuously tuned. So how the twist angle can control the exciton property is one question. And the other question is when the twist angle is very large, can the interlayer exciton still be bright? Okay, so last year there are two groups. They report a new kind of a mixed exciton state we call the hybrid exciton. So the idea is that, for example, in mobillium diselenide and tungsten disulfide, the conduction band of these two layers are almost degenerate. So the electron could coherently tunnel between the two layers. This will lead to the strong coupling between the intralayer and the interlayer exciton. So you can study the exciton properties through the reflection measurement. So there is a strong oscillator strength. So this Sheffield group, they study this kind of a heterobilayer in both CVD transfer sample and exfoliated sample. They observed that these doublets resulted from the strong coupling of intra and interlayer exciton at a small twist angle. But due to the inhomogeneous broadening of those CVD sample, it's hard to resolve the doublets at a larger twist angle. So similarly, this Austin group, they studied this hybrid exciton. Instead of electron tunneling, they found that these two bilayer, their hole can be aligned. The valence band can be aligned with each other. So the hole tunneling can happen, and they can also resolve the doublets. But once again, they didn't show the twist angle dependence from the reflection spectrum. So we decided to use the similar combination, tungsten disulfide and mobillium diselenide. We tried to use all the samples are prepared by the exfoliated sample. So we align the sample very well. This is a crystalline, and you can see the SHG indicated the alignment. And then first we characterize the intralayer exciton transition. Those are A exciton, B exciton from the two monolayers. And when we do the measurement on the heterobilayer, we can see that each of the intralayer exciton will split into a doublet. Okay, this is is agreed with our previous analysis. So the solid line indicated the intralayer exciton transition. Each one you can find an interlayer transition which shared the valence band, but the conduction band come from different layers. Okay, so at this moment, we want to analyze the lowest energy doublets because it's well separated. And this process can be modeled by this coupled oscillator model. And the off-diagonal term is the tunneling rate of the electron between the two layers. We can define the detuning between the interlayer and the intralayer exciton. So what we can learn from the spectrum is the energy difference between the splitted states, and also the oscillator strength of these two states. So from that, we can have two equations, and each of them can be expressed by the coupling strength and the detuning. With that, we can calculate the coupling strength and the detuning. For example, this sample, it showed the tunneling strength is 21 MeV, and the detuning is negative 20.1 MeV, which means the interlayer exciton is at a lower energy compared to the intralayer exciton. So these are aligned sample. It's easy to understand that the momentum conservation is satisfied. But when the twist angle is larger, so in the momentum space, the interlayer exciton and the intralayer exciton are not aligned. So how can they hybridize again? So fortunately, the Moire lattice can provide the band folding, and this band folding at the new Brillouin zone corner, there will be a new interlayer exciton state. It will have the same momentum with the intralayer exciton. Then the coupling can happen again. Compared to the band minimum, this new interlayer exciton will have a larger energy by the kinetic energy. So this energy difference is defined by the Moiré wave vector or the twist angle. So you can imagine you can use the twist angle to continuously tune the detuning between the intra and the interlayer exciton. So this is at 60 degrees, it's well aligned. And when you have sample with larger twist angle, then the detuning become close to 0. And if you continue to increase the twist angle, the interlayer exciton will become at higher energy compared to the intralayer exciton. So those can be easily read from the absorption weight of these two hybrid excitons from your measurement. So we fabricate more samples, both in the 0-degree range or 60-degree range. They all roughly follow this trend and can be explained by our microscopic model. Okay, with that, I would like to conclude. So I showed 3 works about interlayer excitons. First, we demonstrated the high value polarization from interlayer excitons in such a heterobilayer with precise rotation alignment, and also the reduced inhomogeneous broadening. We can resolve the singlet and triplet exciton, and we get a very high degree of polarization. Integrated with the grating structure, we demonstrate a lasing device, and first time we measured the spatial coherence. And here, with the other combination, we demonstrate the Moire hybrid excitons. I would like to thank my collaborators, my advisor at the University of Michigan, Sweden, our PhD students, undergraduate students, collaborator from the UT Austin, and the theoretical collaborator from Maryland, and also our collaborator from and the Japan group provided a very high quality hexagonal polarization. Okay, thank you for your attention. I would like to take questions.
Thank you very much, Long, for being on time. Actually, we have a lot of time for questions, so
okay,
please raise your hand digitally if you have a question. Okay, I can see one question, Feng Li.
Yes, hi, Long. Yes, thanks for the nice talk. I'm just wondering, when you talk about the spatial coherence of the laser, how did you get a conclusion that the spatial coherence has been greatly improved? Because from what I can see from the figures, it doesn't seem to change much.
Yeah.
Yeah, you see, that's
right. Yeah. So below threshold, we because the threshold is very low, we get and the detection wavelength is around 900 nanometer. So with silicon CCD, it's hard to get very nice data, and we collect the data at this power, and above threshold we have more data, and we just compare with the data below threshold. We find the spatial coherence is extended by 2 times. And so on the one hand, it might be limited by the size of the samples, because these are exfoliated samples with a much smaller size compared to the CVD sample.
Yeah, okay, yes. Now I see from the graph there did exist some difference in at least in the forward half maximum of the of your curve.
Okay.
The given maximum. Oh, okay. Yeah, thank you for the answer.
Any more questions? I have one question. Oh, okay. I see you coming up. Guillaume, yeah, go ahead.
Yeah, yes, very short. Well, I was wondering about this laser again. Okay, why is it working in your case somehow? What is the key ingredient with respect to, okay, maybe, I don't know, there was some, for instance, TMD layer put in microcavities, and then people probably try to pump it, and then they had problems with Auger effect, and okay, it did not seem so simple, and why finally is it working now? What is the smoking gun somehow?
So to be honest, we don't know why the monolayer in those cavities can show the lasing, because we work on monolayer with cavity. Usually we get strong coupling. Then because of the strong coupling, the length of the polariton is limited by exciton. So our understanding is that those results should be in the strong coupling region. So anyway, we don't know why. But in the heterobilayer, it's clear that it is in weak coupling region, right? Because the oscillator strength of interlayer exciton is much smaller, so you cannot reach strong coupling. So in that case, the mechanism of lasing is just a conventional semiconductor laser. You need a population inversion. So once you reach that density, the when the gain is over the loss, it's easy to understand lasing can happen. I'm not sure if
I'm sorry, yeah, I don't understand because well, it's exciton lasing. So if it's exciton lasing, you have excitons, and exciton is the opposite of standard gain. So if you have normal gain,
to be precise, it cannot be called exciton lasing because you are close to the Moire density. There is no exciton anymore in that density. So in our case, we really at the density level that the transparency happens. So there is no, we shouldn't call it any exciton in that case when the gain happens.
Okay. Any more questions? Okay, I have one. Even though you're at the Mott or over the Mott transition, you basically have charge separation because you're working with a bilayer. So do you observe the capacitor type of shift that you would expect as you increase the density of carriers?
I see. So, okay. So the dipole-dipole interaction will induce the blue shift. That's what you mean?
Yeah, I mean, you don't need, just basically charging a capacitor, right? You're charging a capacitor because you have separation.
Yeah. I think at this density level, in our case, the lasing happened at 2 microwatts with pulse pumping 80 megahertz. And when we work on the bare heterobilayer to study those the blue shift of this dipole capacitor effect, we found that at very low density, the blue shift is negligibly small, which is in the density range we are working on, I believe.
But you said you're working at the Mott transition density, so it should be. So it should be at high density.
Right. So
you expect to see a significant blue shift, right, of the emission.
Right. In our case, we didn't. Okay, let me show the. So we transferred the heterobilayer onto this kind of anisotropic grating. So in the TM. In the TM component, you can monitor the interlayer exciton behavior, right? And there's no capping mode. So here we see that here we showed the line width and the emission intensity, but with such a broad interlayer exciton emission, I think it's very hard to tell the blue shift from the interlayer exciton peak. Yeah, because we are using the non-encapsulated sample for this device. So more flakes on the grating will affect the capping mode significantly. And we just want to make it a clean, just a 2 TMD bilayer without encapsulation. So the exciton line width is pretty broad. So we can double check the data about the bare exciton blue shift. Yeah, that's a good question. But I think it might be much smaller compared to the inhomogeneous broadening.
Okay, thanks. I think it's for the sake of time we should move to the next talk.